Okay, so we are live also, online, offline. What I am going to do, as of now, I will be having this. I will have only one earphone. Uh, so today we are going to discuss creating neural network using for deep learning using Python. Yesterday, Professor Jadhav he has given what you can say introduction for that, and today I will be continuing with Python, but quite a different what you can say use. So we'll see some of the ANN basics. Clicking there, but actually this is not proper. No? Just give me a minute. Simply should this slide as hand. Okay, I will go by this only. Okay, so coming to today's agenda, that is today we are going to discuss this ANN basics. Then build a neuron using Python, and if time permits, then I have some convolutional neural network I built. So at least that I'll say what I'll say demonstration of that also I will give, but it depends. So first. So why I thought about this thing, that this building a neuron using Python. See, many of you are now. It's like Shashank is there, Gitanjali is there. They are doing their PhD, and they use Python. Or in Python also nowadays we are having this higher level frameworks which are used for building the neural networks. Okay, but at basic, if you want, or if you ask any person that who says that no, I know deep learning or machine learning, what is a neuron and how you build it or how you train a neuron, nobody will say. Very few people. The people who are old in a sense that they have used C programming, C++ programming to build a neuron and then build a network. Very simple network these people used to build. Now I will show you today that how this recurrent networks or this CNNs we can build very fast. Means even no 100 or 4 hidden layer, 5 hidden layers, number of it will take very big image as input that we can easily build. But if we ask any person to build a single neuron and just to train and demonstrate how it works, it becomes very difficult. Even to make this concept to make student understand. So when I was learning this deep learning, this was the initial days when I spent time in understanding how these neural networks are built. So it is like when you are building a full this IT department section, and there are small bricks are used to build that. Unless until we are well versed with how this bricks work, how you can go with a bigger network. So that is the idea. So it starts with the machine learning concept. So briefly we'll discuss machine learning, AI, deep learning, why deep learning, what is the difference, and then we'll again come back how we can do the same thing in Python. So you can ask me, or you can ask the question may come as why we are using Python. If you say why not C, C++, technically Python, here we are going to use pure Python, like base Python, where simple when we say neural network, when our single neuron, simply it is matrix multiplication and how we pass the weights. Okay, the concept of no input vector, output vector, multiplication on updates of weight, and then how we are going to perform the back propagation. So this concept we'll see here, and then how we iterate and what happens when what I can say the network is trained or network is unable to train. So when we say that network is trained, when we say network is not able to train, so that this is called as. So I got one very good article uh, from a person called as Trask. I am Trask, and his article is still there. And I will request the audience that if you have interest in this neural network building, go through that, study that. So this clears the basics concepts of neural network. Okay, so this now we are studying this neural network. Deep learning comes later on, but this parts, this is what we are studying today is, or right now. Maybe machine learning or deep learning will come latter part of this discussion, but machine learning is very basic that we should understand. So it is AI, there is AI, there is ML, and there is deep learning. So machine learning is in very layman's language is that without being explicitly programmed, can can an entity which is computer based solve a problem? If it is able to solve, that is machine learning. This is raw layman's definition. You need not explicitly program that thing. Yes, programming will be there. Okay, programming will be there, but it will be generalized programming. Generalized programming in the sense that we have to put steps for what you can say typical set of problem, not for each and every problem. If you are able to do that, then machines are going to find a way how they are going to reach the target. So that is simply machine learning. So practice of using algorithms to parse data, learn from it, then make determination, prediction something about the world. This is no bookish kind of thing, but without being explicitly programmed. This is the key word when we say machine learning. So machine learns means it learns. It finds its way through the algorithms that you define. So today we are going to discuss two of these basic algorithms. So that's why rather than hand coding software routines, a specific set of instructions to complete. So like here I have teachers which are teaching data structures, and for that data structure you are having no top-down programming where you define what is array, then read that array or whatever array, or I'll say that variables. You define variables, read variables, then you process whatever you maybe create a tree or kind of thing and then program it. So explicit programming is there. So hard coding approach is there to maybe find a largest number, find a smallest number. So steps are there, and that is also a very what you can say or biggest section of the computing where people do work. Okay, it is not like that. We are nowadays people are very much into deep learning, machine learning. If you see, everyone is now, this is buzzword. Okay, so that doesn't mean that every problem can be solved using machine learning or every problem can be solved using deep learning. No, there are specific set of problems which you may approach with machine learning, but there are hundreds and thousands of problems which needs explicit programming. For example, banking, shopping, and there will be coexistence of these technologies. For example, if you go on Amazon and if you want to purchase something, then that is explicit programming. You have to find the list, then search it, then give, then from the database you have to fetch the records and display the price. Fine, that is your normal way of programming. Where is AI or where is machine learning is coming? When Amazon suggests you something. Okay, even that majority of that part is association kind of mining. But beyond that also they are having their strong algorithms which will fetch data from your other activities. They will then comprehend that, and that comprehension will result into what you can say suggestion. Actually, Amazon is not technically using that line to line because Amazon had what its own what you can say product set and knowledge set. But Facebook, Google, they use this kind of. So let it be. So machine learning is simply that without being explicitly programmed, the machine can find solution of a problem given to them. This is a one-line understandable definition. AI and DL. AI is mimicking human activities. Okay. So the way what you can say, what is a human approach a problem, or other than approach in real life, if we are able to make that thing with machine, then it becomes a bigger problem, bigger what you can say domain where now machine can actually chat with you. So chatbots and kind of thing, these are actually going towards AI. So where given a context we can give solutions or expert systems, all these things are AI. And then deep learning. So AI, ML and deep learning, they are actually chronologically connected. Or deep learning is there, machine learning is there, artificial intelligence is there. So one very good slide I have for that. This slide, yeah, you can see where it can be seen here. Artificial intelligence is a bigger set. ML is subset of AI, and deep learning is subset of your machine learning. Okay. Deep learning is subset of your machine learning. Machine learning on its own is a if there is any important point, you may make a note. I am going to share this PPT with you. Don't worry. So you will get this PPT. But important points, if you feel so, you may know. Then if you want this thing, I will share this thing with you. So yes, so here you can see the timeline also, 1950s, 60s, 70s, 80s, 90s, 2010s, and now we are in 2020. And there has been something called as from here 80s to 19, there is one GPUs are there, which are so technically in a way I'll say hardware. So hardware has been playing a key role where this machine learning and deep learning has adopted. There has been another what you can say one good graph I had. What it says that after around 2000, there has been increase in number of publications in machine learning and deep learning. So what is driving that? Mainly the GPUs, TPUs, which are now made available by various vendors. Now NVIDIA is there, then Google is there. Google has got its own this tensor processing units, TPUs are there. So they are having their own hardware. It is not that GPUs are only there. They are having on their proprietary hardware on which this Colab run. We are going to run our program today on Google Colab. So this hardware has been easily available. Today also one of my students was discussing with me that no, with conventional machine, the machine is crashing. So now that program can be shifted to a high performance compute machine that we already have. And the program can be, so that machine is available. So this availability, earlier the mainframes and servers, they were not in everyone's reach. But nowadays even this laptop has got its own GPU. So you can target your coding so that you can explore these algorithms which are having deep learning aspect also. So what is machine learning, deep learning? That we'll briefly discuss in next what you can say part. So AI mimicking human activities, machine learning without being explicitly programmed, we can address some of the problems. And deep learning is that you are having machine learning approach, but you implement more complex network to solve that. So deep learning goes where you are having more complex neural network with hidden layers, increase number of hidden layers. And when you increase the hidden layers, the compute increases exponentially. And normal machines cannot address that. So you have to go for specific machine as I discussed. And these machines are no graphical processing units. So parallelly they process these computations and you can yield the training at a faster rate. Okay, so the training will become faster. Your network can learn faster on this specific hardware, and hardware support will be there. Yeah. So again, coming back to a neural network that we are going to implement today, neural network NN. So here it is basic block. Neural rather than neural network, neuron. Neuron builds neural network. So when we say deep learning or when we say normal machine learning, each of them is going to be consisting of neural networks. They will be dealing with neural networks. It is not only that deep learning has got neural network, machine learning no neural network. No, both of them will have neural network. Both of them will be having neural network. But the way this neural network will be there is different in machine learning and in deep learning. Okay, machine learning because it is a conventional concept. Okay, these neural networks were limited in capacity. But when you go deeper in these neural networks, deep learning concept emerges. Okay, but this concept of deep learning, it is also not new. So that is a separate around from 2000. These people have been working on this. First neuron was proposed in 1958, Robert McCulloch and Pitts model. And then people have been working on that. Various algorithms were proposed. People have built neural networks, and then because now as I said that hardware were available, people could use the what you can say high performance compute machine for implementing what you can say better what different architectures of these neural networks. This deep learning has evolved. So try to understand means if you want to have some takeaway from today's discussions, these deep neural networks and these neural networks, they are not different, because we have seen that this machine learning and deep learning is a subset of that. So these neural networks are there and deep networks are subset of that. If the subset means they are more complex. It is not like the deep networks are there and machine learning is subset of that. No, deep learning is subset of machine learning. Deep learning and algorithm. So yes, when we say neural network, what we actually have inspiration from is that our human brain. Okay, as of now today, even that because of this limitation of time and place, I could not put that slide, but I have that slide separately. So this artificial intelligence or the capacity of this deep learning network, it has evolved over time, and now in maybe in coming next 8 to 10 years we'll reach human brain equivalence of that intelligence machines. As of now we are in progress. Some researchers might have, but it is still in lab. For example, we can say that now Tesla's auto driving car is there. Even your mobile phones, they recognize you. So this is what actually machines are becoming intelligence. They are having some kind of intelligence, but still it is not equivalent to human brain. But we are moving towards that. So this human brain is only inspiring these machines. So inside our brain, we are having something called as this neuron. This gray matter is there. This brain matter is there. That has got this basic. In our, we are having blood cells in our blood. Okay, so that blood is carrying the vital uh, life support in our body. So in our brain, there are different cells, these neurons, and there are billions and billions of neurons are there in our brain, and these neurons, they are interconnected to each other. So here you can see this is a typical neuron cell is there. So you are having nucleus, then you are having this axis of that, and then you are having these axons, branches of that thing, then you are having these dendrites, these cells, and so through these dendrites this neuron connects to other neurons. So these are the, now these, they will be connecting to some different neuron. Here you can say this neuron I am very, and then this dendrites are there, and then they will be connecting to this dendrites, and this network will go on. So what is the strength that human brain is having over the machines is that two things. First of all, we are divine soul, so that is the spiritual aspect, that will come later on. So that soul and body aspect is there, but beyond that, intelligence and consciousness aspect is there. Nobody, no engineer can define that. No engineer can define or quantize that. But as far as the physical body is concerned, it's simple physical, like this physical computer is there. So this is also a machine. So physical machine, if you say that human as a machine, then we are having this one other, this computer or compute that brain, then has got this cells neuron, and they are massively interconnected. So massive interconnects, billions of neurons, and all neurons are massively interconnected at a building level. So forget about consciousness and other things. Okay, so simply if we say that we compare this neuron, what we want to build as deep network. So they are billions of neurons, massively interconnected, electrochemical, this impulse sharing process. So we say that though these dendrites are there, and then dendrites are connected to these axons. So how they connected? In what we are going to implement today is that they are connecting through this weight matrix, and this matrix they multiply. So they are having connections. Okay, we pass this data, but how this neuron pass? They pass the data using electrochemical process. Okay, so electrochemical. So from this point to this point, there is a, what you can say, electrochemical process is happening. So this some chemicals, these neurons are there. These chemicals will be passed from, so one part of the cell to other, and when these two cells actually communicate, they communicate through impulses, and we call this thing neurons are firing, and they fire at very massive rate. And that's why we thought, so maybe now everyone is here, now you are having some thought process going on back of your head, that now today I am having duty, or evening I will do this thing, or why sir is boring, we know everything, and number of things are going on. So our brain has got so various centers, and these neurons are continuous. Only when we are sleeping, they are bit, well say, they are relaxed. They are not stopped. They are just, we are actually, we are having dreaming, and our body is also being controlled when we sleep. So that brain is not completely asleep, but it is relaxed. Why sleep is very important. So this electrochemical process is there, which will carry the data from one neuron to other. But in reality, not in reality, in our, when we say that we inspire from this network, we will build a neuron as, what you can say, a matrix which is communicating, matrix and process, a function which will communicate. Okay, so when we say, when we imitate something like this. Okay, so this is no called as artificial neural network, ANN. So when hereafter, in the context of this discussion, when I say neural network, it is purely ANN. It is not neural. Neural network is there actually inside. Neurons are inside our brain. So pure neural networks are inside our brain. But when, as an engineering viewpoint, when I say neural network, it is simply artificial neural network. So yes, we are having this neuron, or neuron is artificial neuron. So here you can say that transfer function is there, then here you are having inputs, then weights are there, then your output, activation function, threshold. This is the typical structure, very common neuron. You will find this thing in book. So this thing is there, neuron, transfer function, how to build this thing. Nobody is going to discuss, or very few books discuss. If you say, yes, this is neuron, now program this thing, build this thing. and this is one neuron. If I say 10 neurons and then layer of neuron, how to do that? So this is the process that I want to discuss today. If you want to build a neuron, how you will build, how this process, how they do the thing. Okay, but yes, what when I definitely we want to program something, but what actually we are what is, suppose if I want to give you a problem that yes we are having now this is an input vector. So typically suppose for example I am having x1 and x2 as input, and then I am having this output vector that is y, and I will give you relation x1, x2, and y. So 0, 0, 0, 1, 1, 0, and 1, 1. So I will say 0, 0, 0, 1, 1, 1. So this is a famous function. Any of you might remember this thing. What is this called as? This is OR function. So these two inputs are there, x1, x2, y output, and I want to predict this thing. Predict this in a sense, not forget about predicting, classification. So basically when we say neural network, we have a classification aspect. So this problem is there in front of all of us. We have to build a neuron. Here we are having 0, 1, here y is 0, y is 1, here it is x, here it is y. Yeah, sorry, x1 and x2. This is x1, this is x2. So 0, 0, 0, 0, 1, 1, 0, 1, 1, 1, and 1, 1. So sorry, yeah. So this kind of this 0 x1 x2 is 0 1, x1 is 0 1, and so we are having actually one function. Here you can separate with a line. So this is class 1, this is class 2. This is kind of classification is there. So we want to perform this thing. This is what neural networks are supposed to do. So this is a single basic neuron. It will take two input, it will give you one output, and it will say that yes, for this set of input give output 1, for this set of input give output 0. This simple thing you want to you do it, you write a program for that. So how you here C programming experts are there, so you can simply write a program. You have to write a program for this. x1 x2 is given to you, y is given to you, OR function is there. You say OR function is there because you explicitly know it is OR function is there. You will use mathematical function OR there. So I change a bit here. So that I will go later on. But yes, so you understand this is our today's problem. Today we are going to do this thing, implement this thing. We are going to generalize this thing later on. That is a different story. Same network with any kind of. So first of all, as sir rightly said that this is OR function. So you can write simply OR function to program to calculate OR. Done. Your output is there. Okay. Why we need this thing? Why we need this neuron? We don't need that. Okay. So let us move ahead. So yeah. So this neuron also called as perceptron. Okay. So we discussed. So input x. So typically what is happening is that here this is a transfer function output. So what it does, it first of all sums all input dot x1 xi dot wi. These weights are there, inputs are there, and then we pass it to this function f of summation of xi wi plus b. Bias is there, suppose there is bias b, and then we have this thresholding function. So if this summation y value, if function value greater than or equal to 0, output 1, less than 0, output 0, that we can implement here. So this is a nucleus of your cell and output. So this we have to program. Program means what how your neural network functions. This is perceptron model. Is that simply that x1 the weights, these weights are there. So what this network is doing, it will multiply the input vector with weights, give it to this transfer function. We are talking about generalized, not XOR function. Transfer function, then compare it with the threshold, and if it is greater than threshold, it will give output 1 or 1 class. If it is less than threshold, it will give output 0. So there is something called input vector, there is something called as weight vector, there is something called as summation, that is the summation, then given to the transfer function and output. This is actually structure of neuron. When we say we want to write a code, we have to write code for these entities. We have to write code for these entities. So Forget about now. I'll ask you, either you write, or the way you write generalized program, like the discrete structure or this simple C program, or we want to program the same thing using now a neural network. You have to build a neuron. So it is simply building this thing is one part, then training this thing is the next part. We have to update these weights. We have to update these weights in a such a way that we move towards this y. We move towards this y, so that the actual y and calculated y will be same. If actual y and calculated y they are different, then there is an error. So find the error, then update these weights in a such a way that error will get reduced and repeat it again. So this is perceptron. Yeah, here you can say sigmoid neurons is what it will have this sigmoid function. So why sigmoid function? I will tell you. Here you can say this sigmoid function is there. So when I said that you have to move in such a way that the error will be reduced. So what there is always something called as the direction of error. Error direction is there. So sometimes your output will be greater than y, sometimes your actual output actual y, and sometimes your output will be less than y. So we have to update the weight in a such a way that this difference reduces. So if you say that your output is greater than y, and if you update your weight such that this greatness increases, then you are moving in wrong direction. If your output is less than y, and if you update your weights that it further reduces, you are moving in wrong direction. Rather, when your output is greater than y, you have to update weight such that it move towards y. And when your output is less than y, you have to update in a way that you have to move to increase it, this thing. So to increase or to decrease, actually we have to find slope of the function. And when you have to find slope of function, the function should be differentiable. And when you have to have the function which is differentiable, here actually this function, one of the best function is the sigmoid function. Sigmoid function is having self-differential capacity. It can be easily evaluated. Okay, what is differentiation of x? It is 1. So sigmoid differentiation function can be self-described. Okay, so that is another requirement. Here you can say. So here you can see this sigmoid function. Okay, 1 by 1 plus e raised to x. F of this function that we are going to use. And what is this? Here, if I am not wrong, differentiation of this thing is e raised to 1 plus e raised to x is the differential minus 1 e raised to minus x. Here it is minus x. Differential of that. So it is very easy to calculate a differentiation. Okay. So here you can say that's why delta output, when we actually move towards the output, here you are partial differentiation and this weight and bias. So we update the weight in such a way that the slope is the error is reduced. Okay. So these are actually this you have to understand why, because there will be two variation based on this thing. One is normal slope based and there will be gradient descent based. Okay, this concept is important for a single neuron. Again, I will summarize everything in this 2 or 3 sentences. We are having input vector x1, x2. We are having output vector. We have to write a generalized program which will give this output. First thing. Second thing, we build this neuron. Summation of wi xi, okay, plus b, and give it to function that is this sigmoid function. Find output threshold, and then you get output y. If your y and actual y, there will find error. If error is 0, done. You have reached the output, but it will never be 0. So we have to find whether we are having positive, negative error. Accordingly, we have to update using this differentiation. Slope of the error. Why slope of the error? I discussed. When you are moving towards where we are updating, you should be moving towards y, not moving away. So that moving away needs slope of error. Okay. So these things are important. Back propagation. This concept will be there because find error, again update, error, back propagate the error, update, find y, back propagate, update, find y. That will come. Okay. So these definitions we have done. This thing is additional. Now, briefly we'll discuss this hidden layer. deep layers will come. So here we are having, because this also we are going to input layer, your x1, your x2, your x3, suppose now like this thing, xn will be there, and your output y. So here are, this is the input layer, this is the output layer, and this is one single hidden layer, and then these connections are, and this I said that there is in your human brain there is massive interconnection. So actually when we program this thing, there is also interconnection. Here you can see this neuron connected to all this neuron, this neuron connected to all this neuron, this neuron connected to all this one. How we are going to do this thing, how we do this thing. So this all is done using matrices. So from this input layer to the hidden layer, there will be Wij matrix. So I is input layer, J, and for this W1, Wii, when it's a W11, means this neuron 1, this is hidden neuron, this layer 1, and this weight which is here, this weight is W1, the W12, W13, like this thing, this full matrix, two-dimensional matrix will be there. So this hidden layer is there. So you can see now there is only one hidden layer. If we go on adding more and more hidden layer, it becomes deep network. It becomes deep network. Okay. Now we are having here one, what you can say, neuron, and it will give output 1 or 0. So binary classification kind of problem we are discussing. Okay, so why neural network? This is the question. Again, this is another takeaway for if you just want to know why neural network. So there is technically it is called as, there is one concept called as universal approximation theorem. Okay, this is the main thing that you should understand. Why neural network? And I started as, what can I say, one small part of this thing, that when we program neural network, so we have to go for generalized way. So this problem, that one simple thing we'll do today, we'll discuss that when we create a neuron and when we train for one set of input, same network can be trained for different set of input. Same network can be trained for some different set of input. So this network is same, but it can solve any problem, because when I change input, problem changes. It can solve any problem. So this is according to universal approximation theorem, neural network can approximate as well as learn and represent any function given a large layer and desired error margin. So one, I think actually Shankar, one of my friends, I got one discussion day before yesterday that they were having this large control system and this data was there, and this data is given, and we have to find for a given data vector, we have to predict what is the problem. So it's simply, we are actually increasing input vector, and if I am having enough number of training points, I can train the network, same network. So that is a different function, but I say that, okay, you give me 95% accuracy. So desired error rate is 95%, I say. So if I have 10,000 data training point, if I say I want 95% accuracy, I can approximate that problem. That is the beauty of neural network. You can build a neural network which can virtually represent any function. Virtually represent any function. So this is very important. Some functions, and where it becomes important, and all of those who are programmers, and we started with that, is that when you want to solve or you want to write a program or a problem, and you know there is some mathematics behind that, you can write a program, yes or no. But when you know that, rather than when you know that, when you don't know the mathematics behind a problem and you want to solve the problem, so you have to go for approximation theory, and then you apply other models, linear regression or other kind of statistical model. In number of models you will try, and then you will say, okay, this model fits this set of data. Okay, neural networks go beyond that. The statistical models are there. Statistical models means what? Still mathematics is there. They approximate that. So like regression curve, it will fit to maximum points, but not all points. But we say that yes, and that curve has got mathematical equation. Neural network can go beyond that, where mathematical equation is not present, but still they will approximate the input data. So that is another, this is another takeaway. Why neural network? And rather than the problems where the mathematical framework is not available, or mathematical, the expression is not available, and we want to solve the problem, neural networks will be there. Neural networks will help you to solve that problem, any problem. And one of the problem is that face recognition. So I cannot write an equation for my face, but still, or here you can see simply that here when I put this fingerprint here, it is not opening. But I put, it is opening. So there is no equation for these fingers, and but pattern is there, and here is there pattern. So I cannot relate mathematically these two patterns. But I these neural there are neural networks where for this finger or for this finger, they know that yes, this pattern is recognized. So this is what meaning of the statement which is there on the screen, that it can represent or complex this. Okay, so let us move ahead. So today we are actually, there are types, feed forward and recurrent. I am not going to discuss recurrent networks today. Okay, we are going to discuss but this feed forward network, backpropagation network, that we are going to discuss. We are going to build this thing. Okay. So what happens that in these hidden layers, okay, here we are. Now this is the past. What happens where we are having input, we update the weights, okay. Then there may be this hidden network, hidden layers are there. Here we calculate the output. Then actual output is there, desired output is there. We find error E. Then if error E, we have to move in a way that the error is reduced. So we have to find the slope of the error function derivative, and then updates the weight of this hidden layer, hidden layer 1, then input layer, and then process will so forward pass and back propagate the error. Forward pass, back propagate the error. And this thing is called as epoch. One epoch. Okay. So forward pass, calculate output, find the error, find the derivative, back propagate, update the weight. This is one epoch. So in neural network, we say that 100 epochs, 200 epochs. So these are the epochs, that iterations, how many iterations you are going to do to update the weight. So for that, one good animation is there. You can see on the screen how it is doing. So yes, parameter values, then back propagating, updating, again goes back. Again input, then find output, here loss function, derivative, go back. Like this process will continue, update weight, and unless and until the desired error margin is reached. Or you specify, you do go up to 100 epochs, or go up to 200 epochs, or go for 5% accuracy, or 10%, 5% error, 10% error, 2% error, kind of. So always, so when we say this is one part, that how here you can see on the screen, these epochs are uh, okay. Cost function. Yeah. This will come. So now this also is an important thing. Cost function, and then the way we, what you can say, use this cost function for training our network. So cost function means what? How you are going to define the penalty, how you are going to say that how much, rather than defining penalty, how much error you are at, how much my network is costing me between actual input and predicted, actual and predicted, okay, desired, you can say actual output and desired output. So if I say I want to predict 10, but my network, sorry, I should have output 10, but my network is giving 9.7. So there is 0.3 is the error. 0.3 is the error. But how to calculate that? It is that now you say that one number, other number, then you can simply subtract. But there might be vectors. No, either x1, x2, x3, or other than x1, x2, x3, and output will be y1, y2. Then, and there is something called as, when we have higher multi-class classification, so multiple classes are there, then you are having this output is actually recognized yes or no, or maybe finger 1, finger 2, finger 3, and it was recognizing finger 2 recognized, finger 3 recognized, finger 1 recognized, finger 4 it is not recognized here, not part of the class, but yes, it is recognized. Here it is recognizing. So this finger is not recognized, but this finger is recognized. So recognize, recognize, don't recognize. So three classes are there now typically, or 100. Three it has actually uh, enrolled with this machine. So here you are having this yx output and this a, that is your desired output, and then between these two vectors here you can see we are having this absolute error, this mean absolute error is there, you can see that. Okay, so where different, so between actually y1, y2, y3, y4, here y1 cap, y2 cap, y3 cap, y4 cap, it will subtract that thing, then absolute of that difference, square that and sum that. Okay, square that and sum that. So what is this error? The absolute error is there, and if you find the mean of that, mean absolute error, no? Because x1 minus x2, absolute, there's the two functions are the two rows, they will give absolute value, and then square of that, mean square error, sorry, not absolute, mean square error. So mean is there, square of that thing. So this is going to give you always positive value and square of that. So it will, so there are different error, mean absolute error, mean square error, absolute error. Then there is something called as entropy. When there are classes, there is binary entropy. Then there is softmax function is there, categorical cross entropy is there. There are various cost functions depending on what problems you are going to have. Simply you say that yes or no, that today we are going to have 1 or 0. So for such problems, binary, you can other class 0, class 1. You can have binary cross entropy, or simply here this kind of error, because the outputs you can actually measure the difference between them. But when there are a higher number of classes, other things are there, then specific cost function is there will have to be there, because we have to minimize this thing. Here you can see this cost function plot is there, and we have to reach a value where this cost function is having the lowest value. This is 3D plot of cost function. So your error should be always the least. Always you have to, what you can say, update the weight such that this cost function will give the least value. Cost function will give the least value, so that error is 0 and your prediction will be accurate. This is the main reason behind choosing specific cost function, because if you choose a cost function which is not suitable for the problem, you may need a higher iterations, you may have less accuracy, and number of things will be there. So there are, and these things will come in the other parameters of it. Here you can see the typical moment of various cost functions. So, and this methodology, stochastic gradient detect, momentum function, then this energy, I don't, this is a, then adaptive gradient, adaptive delta, and root mean square propagation. So here how this, and this is the error plot. This is the error plot. Here you can say when various iterations are there, how they are going to settle. So settle near 0. When these are values they are overshooting. Here you can see some values are settling here. Okay. So ADA delta is shooting out, RMS prop is shooting out, and energy is shooting out, and but SGD and momentum they are settling here. So depending on, this is just the plot where as per the iterations these things are going to settle, and it should be settled. If they are not settled, means our network is not going to train. So here, so this today we are going to have this demonstration. So without stochastic gradient, it's stochastic gradient. Then tiny network will see 2-layer, 3-layer, and generalized layer. And then the problem here, we are going, actually I started with this thing initially. Now we'll go for demonstration. So here we are having this exclusive OR function. I told that this function, inclusive or exclusive OR. So idea is that, see, I started with this OR function is there. So there exists a line which separate these classes. Can you see? Y equal to mx plus b is separating these two classes. But for this exclusive OR, can you see there is no single line? So 1 is here, 1 is here, 0 is here, 0 is here. Can you draw one line only which will separate this? It is not possible. It is not. So this problem is called as here linearly separable problem. Linearly separable problem, because one function exists which can separate. This is non-linearly separable problem. This is not linearly separable. Linearly separable problem, we have to have function something like this. Yes, it is separate. But neural network can do this thing. But simple neural network won't do. We have to go for higher network. So how it is doing? Here you can see. So AND function, OR function, here you can see outputs. Here separation possible. But here XOR function is there. It is either XOR or XNOR. Separation is not possible. Here you can see. One single line cannot separate. You must have two lines. So we have to implement this all function we'll implement this thing using neuron. So let us move on. Now actual this, if time permits, CNN I will discuss, otherwise. So yes, I will share this tab. Just P. Display. Now you should be able to see. Yes. मगाशी दिसत होता तुम्हाला? We were having a slide दिसत होता ना मगाशी? We were having a slide, na? Okay. Because now this online and these things are there. So yeah. Now idea is that here I am using Google Colab. This screen is of Google Colab. Yesterday the demonstration which was given to you, that was on native Python compiler. Okay, for those who are new. And I prefer for this deep learning, if you want to go for study Python, work on Python, fine, you can always go for this local Python, install Python on local machine, run, that is always good. But when you want to go for deep learning and deep learning based study, now I recommend that use Google Colab. It is always better, because and you can do, if it can handle deep network and deep programming, then simple Python also it can handle all, and better. I mean, I will show you some of the things later on. Yesterday sir has given you some demonstration. I will also give you some continuation of that data exploration in Python, how it is possible. I will show. But before going to that, here we'll have today's discussion. So here this is the article. Maybe if you want this code, I will share. So this here you can, this article link is there. I am trust GitHub, and on this person has shared. I have just modified that code and implemented that code in Python. Modified that with comments and then flexibility, and added more networks, more layers, and more kind of combinations to that. So in a faster way we'll go. Okay. So yes, here. Yeah, so we are having this function. Here you can see array x1, x2, x3, and here this is, I will show you that we'll have this OR function first. So this is 1, this is, yeah. So even number of ones 0, odd number of ones 1. So this is why. And yesterday sir has mentioned numpy. So we are using numpy in numpy as np. Uh, zoom. येते zoom. So here you can see this numpy. Your yesterday sir mentioned that array process. So in Python, directly we are using importing numpy as np, and in creating an array. So that's why Python I prefer as compared to C. So simply you can array and then this is transpose. So we are having this array x as this 001, 1011, and this array. 4 rows are there. Of this rows you can see here, and this y array, this column array, you can see transpose at the end, it is there, transpose. Then this synapse means what? From this layer 1 to layer 2, when actually this data is going, is actually synapses are there, which actually these arrays they actually update. Okay, so here you can see this 3441. What is this dimension? You don't worry as of now. Don't worry. This idea is that you are I am having input layer of 3 neurons. Okay, input layer of, you can say, input x1, x2, x3 is there, right? And then there is output layer. Output layer, how many output is there? 1, y. Output is 1. Okay, and then your then size is 3 into 4, 4 into 1. Okay, the synapse size. Okay, so there is simply 3 and output 1 is there. Simple one network means it is called as single neuron. Typically we have built single neuron is having 3 input and 1 output, and we are calculating synapse and these things in between, and you don't worry about a single neuron we are building. Okay, but how to build it is an idea. Then second thing is that these are the epochs. I am specifying epochs. 600 epochs you perform. We can perform less also, we can perform more also. Why 600? We'll see. Okay, then first is that what we are doing, L1, layer 1 output. Layer 1 output. What we are doing, synapse 0. Okay, this matrix we created initially with random weights. Random weights means between 0 to 1, it will generate a matrix of 3 into 4 sides. Okay, 3 to 4 means what? 3 rows, 4 columns. Okay, 3 rows, 4 columns, random weights. Okay, and then it will multiply this. So you are having y. So So every row of that thing will be multiplied with y column. Take multiplication, sum that thing, output will be calculated. So that is the meaning here. Here you can see this here. So np dot dot, your input, np dot product, you are calculating dot product. X is your input. How many values are x there? X1, x2, x3, 3. So 3, 3, 3, 3. 4 rows are there. At a time, only one vector will go. So 3x. So 3x it goes. It we have to multiply it with synapse. How many rows are there in 3 rows and 4 columns? So 3 rows it will be transposed. Now x is transposed. Multiply with rows. It will calculate that. Dot product will be there. So this is L1. So beyond that, here you can see. And then what you can see here, np.exp. What is the meaning of np.exe? 1 divided by 1 plus. So that is sigmoid function. That is sigmoid function. Sum of all, summation of all that thing. But we have that means what? I will come back to slide. I will show you that. We will understand what we are doing here. When we multiply that thing, here we are doing this thing. So when I'm having this xi, wi1, so this part input into weights. Okay, this part is here, input into weights. Okay, second thing, summation of this thing and transfer function, summation and transfer function. This part is here. Because 1 upon 1 plus this summation part goes here when we multiply. Summation part, when we multiply a matrix, it sums that 3 x1 x2 x3 multiplied, it sums and gives one single value. That single value is given to exponential 1 upon 1 plus ex, means what? This is what? Transfer function. Transfer function. So L1, then L2. What is L2 I am doing? Here you can see output layer. Output layer. L1 into sin1. So this L1, output of this is given to the panel, means actually here this summation, and then here output layer. Actually what is happening here is weights 1, again there is one set of weights is taken here. It is taken because layers are there. No? When from input layer to the output input layer, we have this thing. So from this to this, and there is one. So here input to first layer to output. Try to understand. So that is, this is one synopsis is existing here, and technically second synopsis is existing here. Here. So this is syn 1, synapse 1, and that is synapse 2. So this is synapse 1. Here you can say syn 0. Here they are actually I am taking synapse 0, synapse 1. So technically synapse 0 is here. What is updates? And synapse 1 is here. What is updates? So two times. So input to this neuron and this neuron to output. When it propagates again output to this neuron to input. Like this thing it will propagate. So technically there is one neuron only. One single neuron we are talking about. In Keras and other thing, hundreds of neurons we built. So we are programming one single neuron. It is not even layer yet. Layers of neuron is not there. These are the nodes. These are the nodes. This is not layer. These are nodes. And this is single neuron only. When we'll increase this thing, there will be nodes and layers. Okay. One more layer will come, and in each layer, how many neurons will be there? That we'll have to define. So as of now, we are talking about one single neuron, and that's why it has got, it is having problem. Okay, so these are the node 1, node 2, node 3, node 4, then summation, then output. This we are implementing. This simply we are implementing. Okay, so 4 node, this x1, x2, x3. 3 nodes are there and one output is there. This we are implementing. Okay, then now here it is the thing, delta. So delta here L2 divided by 1 minus L2. Here you got. So what is this thing? Actually it is a derivative. Because we are using sigmoid function, derivative of sigmoid function is x by 1 plus x. 1 upon 1 plus e raised to minus x is sigmoid function, and derivative of that is same. Differentiation of that is defined here. Okay. So here this is the derivative y minus L2. Here we are finding out what is the error. How much is the error? Here you can see error. This is actual output. The desired output. This is actual output, predicted output. And there is difference. We are finding difference. And this is the derivative. This is the derivative. Then we got the delta. Delta output, E, error. And then we use this, what you can say, delta will be multiplied with this synopsis for updates of weight. And here you can see L1 delta. So always for every layer, we find the derivative and multiply with synopsis. Go back. Now this part is called as finding out the delta. And then this part is called as back propagation, where synapses are updated. Synapses 1, L1 dot L2 delta. Output delta is added to output synapse, and from that L1 delta, here you can say L1 delta, it will calculate by L2 delta, here synapse 1 dot C. So this becomes actually complex here, but let it be. Synapse 1 and synapse 0 are updated here. The back propagation is complete here. And then with this synapse 0 and synapse 1, we go back, and here you can see, again find, again take the same data, multiply that, and find new L1 and L2. And this process will continue. Continue till what? Till we reach. So here what is happening, what I am doing, so this is a simple program that we are going to iteratively do. I have modified that thing so that you will get insight what is happening in between. So here we are having this program. So what I am doing, I am calculating in between error also. Here you can see this error vector was there. So here you can see L1 error I am calculating, then here this error dot append, this I am having this, I am getting the list, I am generating a list of error, I am appending that this error to the list, and I will plot that error, I will plot that error. So when we run this thing, here you can say we'll have a simple function, linearly separable problem. When we run this thing, here you can see what is happening. Here after 100 iteration, this error is going 0, and here it is almost 0 network edge. When error becomes 0, means your network is able to predict the things accurately. Here you can see output after training. So what you wanted? What you wanted for this set here 1101. You wanted this thing for this set of input. After 600 epochs, what it is predicting? 1101, 0.948, 0.99, 0.05, 0.95. This the network has predicted after 600 epochs. After 600 epochs, the network has predicted. Now let us introduce non-linearity to this. When what happens for this single neuron, we introduce non-linearity. We'll see. So I am going to add non-linearity there. Now you can have any function. 110 simple function is there. Another function. Now I change this function, but the same problem, same network is able to predict that. If I change this vector in a way that it is linearly separable, 0, 0, 0, 1, and function, same network. Here actually still some error is there. What I will do, I will increase this epochs, and this problem will solve. This will train. Here you can see. This network is trained. Now let us add non-linearity to this, and what happens we'll see. So non-linearity means what? We'll have this function as XOR function. So 1001. If I have this thing, if I fire up, see what is happening? Can anyone tell what is happening? Error is reducing? No, it is there only. The network is not able to classify this single neuron. This single neuron is not able to classify this function. Why? Because single neurons, these perceptrons, they will classify only linearly separable problem. Single perceptron. And this is non-linear problem. So it won't learn. Even if you have 10,000 epochs, it will not run. Generally, the 2,000 epochs are there. We have this 10,000. It will run for 10,000 epochs. It won't run. It won't learn. This is not so. Linearly separable problem cannot be solved using single neuron. So what we have to do is that now we have to have hidden layers. Single layer cannot solve that problem. So now we have to go deeper. So we have to go deeper to solve a non-linearly separable problem. So we'll have one hidden layer. We'll add one hidden layer. So that's why 3-layer network. This is initially what we have seen. 2-layer. 2-layer means input and output. One input layer and directly output layer. So technically it is not a layer. It is single layer only. So we call it a 2-layer. Input layer, output layer. Now hidden layer means what? Input, hidden, output. Okay. So we are adding, we'll add now one hidden layer. So 3-layer network. So here again the problem is same. There you can say 1001. We'll start with non-linear problem first. Okay. So linearly separable problem first. Here how this non-linear one hidden layer is added. Here you can see L0 is X, L1, L2. Yes. So earlier it was L0 and L1. Now L0, L1, L2. So this is hidden layer. This is output layer. Okay. So here you can see y L2 error means what? Y minus L2. L2 is output. Error is y minus, and then same process will go. But now this error will be calculated 2 times. Output to L2, L2 to L1, L1 to input. So that's why there will be how many synapses? 3 synapses. Here you can see. Synapse 0, synapse 1, and 2 synapses. Syn 1, syn 0. Yeah. L1 delta, L2 delta. Input and output. 2 synapses I am taking. We check. Yeah. L2 delta error append. Sin 0 sin 1 sin 2. नाही बरोबर आहे बरोबर आहे इकडे हिअर 4 लेअरला sin 0 sin 1 sin 2 बरोबर आहे synapse 0 synapse 1 ह्याला आम्ही एक redundantly synapse यूज केला आहे synapse 0 only here you can see in case of your a tiny network here there is only synapse 0 single neuron okay I just mistakenly done that and then when there is one 3-layer network is there na there are 2 layers single synapse is there, single synapse function, Wij, and there are two Wij. One hidden network is there, so input to hidden, hidden to output. Sorry, that like this thing it goes on. So two synapse functions are there. Because actually I scrolled one layer additionally down. So three-layer network, three-layer neural network. One hidden layer is there, and now when we give this, first of all, let us give now linearly separable problem. Here it is training. Here you can see this is error 2 and error 1 means output layer error and then hidden layer error. Okay, it is training. It is training. So any kind of what you can say linearly separable problem it will train now. So here even AND function if we give 0 0 0 1, this is AND function. This is training. Now let us give non-linear problem. Let us give non-linear problem to this. 1 0 0 1. Now let us see whether it is able to take. It is training. When we add this hidden layer, it can classify now non-linearly separable. There because this problem is not linearly separable. Two functions are required, but still it is classified easily. So that is the power. Now when we added one hidden layer, it was able to classify non-linear problem. Was able to classify non-linear problem. So same thing will now continue. 4 synapse will be synapse 0, synapse 1, synapse 2, and here 4 errors, and here you can see this output error, then layer 1, layer 2, this is layer 3. So layer 1, layer 2, layer 3, final errors, and this network will train delta 1, delta 2 also. So you can see now these functions they are getting complex, but still network is getting trained. So when you go on now this is what simple where back propagation error and differential of error we are ready. So what is the modification here is that stochastic gradient descent. Okay, gradient descent, gradient descent and stochastic gradient descent. Where gradient descent we are actually having the differential of error in a complex way. More complex function is there. So here you can see layer 1 delta, synapse 1 multiplication and differential, complex differential we are adding, and in the direction of that gradient means what we have the slope, what you can say it is not simply the differential, small differential, but error function is there, in what direction error is moving, and then that error we have that alpha also, learning parameter also, learning parameter, hidden dimensional learning parameter means what, the momentum, it is not only that slope. Actually, yeah, here you can see. So this is for SGD. We'll have this. Yeah, this is the article. Yeah. So when the slope and momentum is there, here you can see we are moving in the direction of error. So this is the error direction. This is where you move. But what happens that sometimes there is overshooting also. When you have this thing here, you can see. So when overshooting, undershooting, so two things are the momentum will limit this overshooting, undershooting, and slope will gradually take you, here you can see the higher slope, you can see in a faster way. Here your small slope, small way. And again, this alpha will also dampening factor. It will act as learning rate. So when alpha is high, network will learn at faster rate. When alpha is low, you will need more epochs, but smoother learning curve will be there. Okay. So here actually this gradient descent function is there. And what is stochastic gradient descent? Here you can see. Actually, gradient descent, we try to find the minimum, local minima here and reach that local minima. But actually in the learning curve, there can be multiple local minima. So if you are looking at bigger picture, you may result here, but actual minima is here. But so many points are there, you will have to try them. So what stochastic gradient descent will do? It will stochastically choose, randomly choose the point. And then because of that thing, there are more chances that you will reach to the actual minimum. Actual minimum. Otherwise, we'll go by simply gradient descent. You may reach the local minima only. You may not reach the global minimum, which is the actual minimum. Here actually, so you will have error reduced to 90%, but you won't reach 95, 97%. But with stochastic gradient descent, definitely there are more chances that you will reach here over the iteration. So that is the meaning of this. Here you can see. So stochastically it will choose between different minima and then it will run that thing. So here, that's why here the stochastic gradient descent part is added here. Here the stochastic gradient descent part. And two inputs are there. So again this linearly separable problem is there with SGD, stochastic gradient descent, sigmoid output to derivative. This is now actually we are having this now slope of the sigmoid and SGD part is there. So this and then this definition of sigmoid here, output to derivative. So using this thing, we are implementing SGD. So here after 600, here you can see now the function is getting what you can say learning. So I will improve the parameter, increase the iterations, and with SGD still learning is there. For 10 for iteration. See, yeah. Still this network with SGD, it is not learning. So we'll have additional layer which will help us to learn the same. We have three inputs, same complex. Alpha is learning momentum parameter is there, and here you can see the network learning with SGD, hidden layers. Now with the same concept, what I have done, we'll go for the generalized one. Yeah. Here, what we'll do, hidden size. So hidden, your layer is there. How many hidden layers you want? So we'll start with simpler one, that 8 hidden layers. And here you can see. Now earlier we were up to 1 hidden layer, 2 hidden layer, 3, now 8. And then there is another generalization is that neurons. So in every layer, how many neurons? So 2 layer, 4 layer, 5, 5, 6, 7. So in here also, in here also. So that modification also I have done. So here you can see. Huh? Number of what? No. S0, S1, S2 will also increase. Yes, yes. I will show you that. Multiple number of outputs and generalize I will show. Flexible number of hidden layer. Actually, for that plotting is there or not? I don't know. Yes, it is there. Here you can see. So hidden size, 32 neurons in one layer. Such 8 layers. Such 8 layers. Number of outputs 2. Number of inputs 3. Range of calculation epochs 5000 epochs. Okay, and alpha and intervals that I have internally used. Then here you can see now. Here you can see input synapse, hidden synapse. Here you can see hidden synapse. Synapse for hidden layers. So this is dynamically calculated now. Hidden layers, number of hidden layers plus 2 plus hidden size plus hidden size. Three-dimensional. Three-dimensional array is there which will store the synapse. So this is actually we are building a neural network. Inside what is there? So this is a three-dimensional array which will store the weights and this weight and the synapse output. So synapse array for output, synapse array for input, and synapse array for hidden network. And depending on your flexibility size, flexible layers, this array. So all this training and weight, it will be updated. Actually, we build the network here. This array will define the weights, and then here calculation is here. So here you can see layer equal to 1, and then other layers into range 1 into hidden layers plus 1. So in the hidden layers we are going to reach at each hidden layer, calculate, update, back propagate, calculate, update, back propagate. So this is a bigger what you can say process now. So when we now, that's why here only output final layer is plotted and function is same. Function here is 0 1 1 0 1 0 0 1, non-linear function. So if I train this thing, so virtually it can train for any network. Here you can see now almost after 4000 epochs this network is learning. If I change this thing also, this network can learn. Now any function universal, we just discussed now universal approximation theorem. Here you can see, as it is now linearly separable, the learning curve is more smoother, and network is learning after 2500 epochs. But when we have this non-linear problem, or other way around, we'll take 1 0 0 1 0 1 1 inverse of that earlier one. If we give this, here you can see after 4000 arrays the network is learning. So this is generalized network. Now you can specify here how many hidden layer you want. I will say that now hidden size I will have 32 no hidden layers. Actually if I increase the hidden layers na, again this becomes unstable. Let us see whether it is learning or not. 16 hidden layers. Yeah, it is not converging because it takes time to converge, and this much power network is also not required. Let us see whether it learns for 12 hidden layers. Because huge number of epochs will be required there. 7, I will reduce this layer to suppose 6. Here now when you reduce, because see what happens, I will discuss that point also. Here it is learning. So when this layers increase, hidden layer, hidden size increase, this normal way of handling the weight doesn't work there. You have to go for sophisticated ways to manage and train the network, train the layers. Or otherwise number of epochs will be lost. 20,000 epochs, 30,000 epochs will have to be there. Then network will converge for that problem. So this is fully generalized, what you can say, network that can be seen here. Full flexible number of hidden layers, flexible number of what you can say neurons, and your layer network is built. This is last or what you can say quantification, that is that how Google is doing now. When from this thing we build a class, means what, this neuron class. Here you can say class HK, this neural network is there, this neural network class, backpropagation defined, and then we are actually building it. Here you can say 16, this is the learning rate, then number of neurons, then hidden layers, epochs, and then train it. Model dot feed forward, model dot back propagate, and get accuracy. Train that. If we do this thing, here you can see training accuracy is almost 100%. Almost this network is able to predict that. So this is what Keras and TensorFlow they do. At the end, they train and a class is built, and then you using that thing, you do it and say the network is learned. So this is input. Keras, TensorFlow, we use this. So we are not bothered about what is inside. Simply, what you do, use this. Just build model X, Y, 16 hidden 4 layer. But backside, this many commands. What we just built, that is there. Yeah, this training and so from flexible numbers kind of. So here, yes, we complete this part. I will briefly discuss one yesterday what sir is there. We'll briefly discuss that thing. So I'll stop live.